Alright, so last video we described what a surface element looks like on a curved surface. Um, if you remember, ds, we decided ds was equal to the square root of dz dx squared plus dz dy squared plus 1, and then we had a dx dy outside the integral. Which we could also write as dA. For now, we'll just leave it as dx dy. Well, anyhow, what we were doing, if you remember, is we took a look at some curved surface between some boundaries. Maybe it looks something like that. And it had boundaries on the x-axis, x1 and x2, and boundaries on the y-axis, y1. Let's say it's there, and y2. And that left a shadow region beneath it. So anyhow, the whole point of ds was to take a look at a small little chunk on the surface. And we went ahead and made a derivation for ds here. Now the question is, we don't just want to find the surface area, we want to find the flux going through the surface. So if you'll remember, when we looked at surface area, we were finding the area of small parallelograms. Well, now what we're doing is we're using the normal vector. I use little n. And so this is the unit normal vector to this surface. This surface has area ds. And remember, ds, before we took the magnitude of it, points in the direction of the normal. And so what we end up with here is, if we want to find the flux caused by some field f at that point, we take the dot product, so we integrate. It's the double integral of the field dotted with the normal vector times ds. Now, like I said, ds actually does in and of itself carry the information of the normal vector. So if you left ds as a vector, you could technically write this as f dot ds with a vector sign over it, but because we took the magnitude of it, we need to add in a normal vector again and then do ds like that. Now, how do we find this normal vector? Well, you'll recall that we were able to utilize, with a function of f of x and y, which would be equal to z, what we were able to do was subtract z over to the other side and call this a function of x, y, and z equal to f of xy minus z. Now, once we did that trick, we were able to take the gradient of f, x, y, and z, and we found that that gradient of that function, that scalar function, was always normal to the surface. Then we wanted to make it a unit vector, so we divided by its magnitude. And so here's another use for the gradient, is to find the normal vector to a surface. And so you can replace the normal vector to the surface in here with the gradient of f divided by its magnitude. And so this is not too much of a step up to what we've been doing. It's kind of getting a little bit easier to imagine these concepts. Just remember that if you're ever confused about what a theorem is saying, draw its smallest component, because in calculus we're always looking at small components and arbitrary ideas, and then we integrate those small components and arbitrary ideas across a surface or a line or a volume. And so just look at the smallest component. That's all you need to know to do good calculus. So I'll see you next video, and I hope this was helpful.